Welcome to this introduction to sequences. We start with a simple example. Let's have a look at a sheet of paper. If I fold it like this, the new size is half the original size. If I fold it again, the size is only a quarter of the original size. If I would continue folding like this, it's clear that the next reduction factor is 1 over 8, followed by 1 over 16, and so on. Such a list of numbers is called a sequence. The first term is denoted as a sub 1, the second term as a sub 2, the third as a sub 3, and so on. In general, the nth term is denoted as a sub n. If we know a certain term in this list, the next term is easily determined by dividing the current term by 2. This is called a recursive definition of the sequence. If we know the initial term, then the others easily follow. Here, the first term is 1/2, so the second term is obtained by dividing it by 2, giving 1 over 4. Again, dividing by 2 gives 1 over 8, etc. In this case, the sequence can also be defined by an explicit formula. The nth element is obtained by raising 1/2 to the power n. Also, this definition leads to the sequence 1 over 2, 1 over 4, 1 over 8, and so on. We are already familiar with functions, mapping a real number x to a value fx. In fact, a sequence is also such a function, but then with a special domain, the set of positive integers, so 1, 2, 3, 4, 5, etc. In order to indicate that the domain consists of integers only, we often use the variable n instead of x. Since a function can be depicted by a graph, we can do this for a sequence as well. Along the horizontal axis, we put the integers n, and in the vertical direction, the corresponding values a sub n. For the sequence given by the formula, 2 times n divided by n plus 1, setting n is 1 gives 2 over 2, which is equal to 1. N is 2 gives 4 over 3. N is 3 gives 6 over 4, which is 1/2, and so on. In particular, it is interesting to know how a sequence behaves when n gets large. In order to investigate this, we can evaluate the limit of a sub n when n approaches infinity. For the example on the slide, we can easily find a solution by dividing both the numerator and the denominator by n, which gives that the limit equals 2. In the picture, this is indicated by the dashed horizontal line. In general, we say that a sequence has limit L if a sub n gets very close to L when n becomes large. If such an L exists, then the sequence is said to be convergent. If such a number L does not exist, then the sequence is divergent. Earlier in this presentation, we already saw an example of a convergent sequence. Here's another one. In contrast to the previous example, sequence values now appear both below and above the horizontal line representing the limit value L. This is okay, as long as the values approach L when n gets large. When there's unbounded growth, the sequence does not approach a limit value, and thus it is divergent. However, note that it is not necessary that a sequence grows to plus or minus infinity in order to be divergent. The green example sequence keeps on alternating between a small positive and a small negative value, but it does not converge to a single fixed value. Therefore, also this sequence is divergent. Let's end by revisiting the example we started with. Note that this sequence has limit 0 and thus it is convergent. That's all for now. Hopefully the basics of sequences are clear. Still, there's much more to be explored. Enjoy!